Welcome back, AP. 14.3, we're going to look at a new type of expression called rate law. Rate laws is not the same as the previous video rate law expression. Okay, so just because it's called rate law expression, it's not the same as rate expression. We have several learning objectives that we need to be able to master in Unit 5.2 AP Daily. Some key things are we're going to be looking at experimental data. We're going to be looking at how to write a rate law expression. And then we have a new letter coming in called rate constant, little k. Okay, and I'm going to put over here, little k. So take a minute, read, annotate, so you see what learning objectives we need to master, and how is rate law and concentration related to each other. Okay, so one of the components that we looked at in 14.2 was concentration, changing concentration by increasing moles. Okay, so if you want more, if you have a higher concentration, that means you have more moles of the component, which means it leads to more collisions. Okay, so in general, to make something go faster, I either can increase the reactant's concentration, and then that'll increase the rate, or decrease the concentration of the reactants, and then also the rates would decrease. Okay, so obviously a direct relationship. We often examine the effect of concentration on reaction rates by measuring the way in which the reaction rate at the beginning of the reaction, it always depends on the reactants. Okay, so you're going to see in this expression, we're going to kind of exclude the products for a while. Let's take the overall equation, just generic equation. X plus Y gives you Z plus W. Okay, in a rate law, and like I said, sometimes they call it rate law expression. Okay, this would be the rate law. Okay, so you write the word rate, then you have this little k. Okay, and I even have the little description of it. Little k is called a rate constant. It's a small k, not a big K, because big K is Kelvin. It is very dependent on temperature. So if K changes, actually let me rewind that. If temperature changes, then you have a new K, a new rate constant. Okay, so we like to keep temperature constant when we're doing these calculations. Also, K, the units will change depending on orders, and I'll get to the part that I mean by orders. Okay, so K is very dependent on temperature and the orders. Then we have brackets X. Okay, so obviously X and Y, they are the reactants. Okay, and then you have this little m and this little n. Well, these are called orders. And in order to determine the orders, we need data. We can only do this experimentally. Okay, so you can't use the balanced equation as in coefficients, aka coefficients, to determine orders. Okay, doesn't work like that. But if I add up m plus n, we call that the overall order of the reaction. So basically you just add them all up. So if I had a rate law that was like x and y, that means x is first order, y is first order, so 1 plus 1 is 2. Apologies for the dogs. All right, let's start again. If you have a rate of concentration of x to the first power, y to the first power, then you have an overall order of 2. And if your x is to the second power, y is to the first, well, 2 plus 1 is 3. And same thing if you have the order on 2 for the y and x is 1, same thing as 3. Okay, so you're just adding up the orders. But these values, you need data. So how do we determine this? So I have a simple way, and I call it Rodriguez rules. You have to look at data as in two trials, where the concentration of the reactant is held constant. Okay, so one of the reactants, concentration has to stay constant. The other reactant has to change. So then you look at the 2 and ask yourself, did it double? Did it triple? What happened to it? And then you look at the factor when it has to do with the rate. How was the rate affected? Okay, it's very easy math. I know this was very confusing, okay, but this is how you solve for it. So think of concentration as in, if you double, think of the concentration as 2. So if your concentration doubled, okay, did changing the concentration have 0 effect? Well, if it has no effect, you could change concentration all day long, but if the rate didn't change, no matter what happened to concentration, then it's no effect. It's 0 order. If you double the rate and the other reactant was double, okay, so 2 to some power equals 2, so that's called first power, okay. If the rate was quadrupled, okay, and the concentration was doubled, so 2 to what power is 4, so then we call that second order. And same thing, if you have 2 to some power equals 8, well, we call that third order. The orders can go up as high as they want. Usually we don't go past 3, but I've seen a 4 out there in the world, okay, but usually the ones we practice go up to either 0, first, second, or third. So how do we work these rules? Okay, so let me show you the steps. So step number one, find 2 trials where the concentration of one of the reactants is constant. Okay, so I have concentration X and I have concentration Y. And these are called experiments, aka these are trials. So I had experiment 1, 2, and 3. I'm going to solve for X. Okay, so when I want to solve for X, okay, so solving for X, I have to change X while Y stays constant. So if you notice right here for Y, these stayed, oops, don't know why it's doing a triangle, they stayed constant, okay? So I want to look at, I'm going to tell AP, I'm going to use experiments 1 and 2, okay? So I'm going to use these 2. So one of the concentration has to stay constant. Now focus on the other reactant, aka X. Ask yourself what happened to concentration and how did it affect the rate, okay? So I'm looking at these 2 values and then I'm going to look at what happened to rate. So what you do is you put the bigger number, so this is the concentration, oops, I forgot a 0, over 0.00500. All right, let's get some calculators. And then equals, same thing with the rate. So I'm going to say 2 and then 1.00. So this side is my concentration, this side is my rate, okay? So 0.0100 divided by 0.005. All right, well, that's a whole number 2, okay? And obviously 2 divided by 1 is 2. So this concentration to some power equals 2. Well, then that means this is first order. So automatically right there, and actually I'm going to call it A. Let me erase this in, because right there we said A. So I'm going to call it A. Okay, so right now I know X is first order, right there. Okay, now I'm going to do this in a different color. I now have to solve for what happened to Y. Now, what 2 experiments can you use where Y changed, but X had to stay constant? Okay, so let me erase my little brackets up here. Okay, so X stays constant right here, but Y changes and the rate changed. So there was an effect. Okay, so using experiments, so sorry. All right, solving for Y. Sorry for the dogs. So for Y, I'm going to use experiment 1 and 3. And experiment 1 and 3, I'm going to take Y because it changes. So my concentration, 0.0250 over 0.0125. okay? And how my rate went from 1.00 to 0.500, okay? So remember, this is concentration. Let me get my calculator. It looks like it's 2, but let's don't start doing math in our heads. All right, so this side is going to be 2. So 2, and I'm going to put a B because we're solving for the y. And then 1 divided by 0.5. Well, that looks like 2 also. All right, so then that means B is first order. Okay? All right, so let's make some notes so far. Okay? Whoever you're solving for, the X, that means the concentrations have to change. As the other concentration is constant. Okay? When you're doing the math, you always want to do the math, the bigger value over the smaller value. And the reason why is because we want whole numbers greater than 1. Okay? We're not looking for decimal or fractions. Okay? So I'm going to say whole numbers as much as possible. Okay, but you could get a decimal. We just want a number that is greater than 1. Okay, that's the key to it. We don't want a number that's less than 1. So in the description, determine the following. All right, the orders of the reaction with respect to each reactant. All right, we figured out that each one is first order. What's the overall order? Okay, so we're going to write overall order. Well, is 1 plus 1. Don't think that's too hard. So 2. Okay, so this is order for that one, and that is the order for that one. Write the rate law expression. So remember the rate law expression, we write the word rate, okay, little k, and then concentration of X to the first power, and concentration of Y to the first power. So I'm just going to write a little note over here. This is rate law. Just don't write the word law in the expression. Okay? All right, so far so good. Determine the rate constant. Okay? So if this is our expression, how do we solve for K? All right? So to solve for K, pick any experiment. And why can you pick any experiment? Since temperature is constant, the K will be the same for every experiment. For every experiment. Okay? So I always like to pick the first one because it's the first one. Okay? So I'm going to say experiment 1. Okay? And basically just get all the values that you need from experiment 1. So I have my rate. So my rate value right there, 1.00. And notice the units, M over S. Okay? Make sure that M is capitalized versus S lowercase. I don't know what K is, so I'm just going to write K. My concentration of X, 0.00500, big M. Okay, and it's to the first power. And then my Y, 0.0250, big M. Okay? So this is called algebra, ladies and gentlemen. So first thing you want to do, let's go ahead and take care of this. If you had any squares or cubes, you would take care of that. But they're both 1 and 1, which means we're just going to multiply these two numbers together. So 0.00500 times 0.0250. Okay? So I'm going to get a really small number, 1.25 times 10 to the negative 4. But what about the units? If you multiply the numbers, the units get multiplied by 2. So M squared. Okay, so I don't mean the units don't get multiplied by 2, as in the units get multiplied together also. Okay, not multiplied by 2. So M times M becomes M squared. So then you still have little k, and then you have 1.00 M over S. Well, to solve for k, I need to divide each side by this 1.25 to the negative 5. So I'm going to take 1.00, big M over S, divide 1.25 to the negative 4. M squared. Oops, let me fix that. M squared. Okay? Doesn't seem too hard in math. Take the two numbers, divide 1.00, divide 1.25, E button, negative 4, and big number. It looks like we need 3 sig figs, and my calculator says 8,000. So we're going to have to go scientific notation. So 8.00 times 10 to the third. Now the tricky part, okay? Notice in the directions, what's the unit of the rate constant? Sometimes AP, they'll, instead of asking you to calculate, they may ask just what's the units. That sometimes struggles students more than the math. Well, let's take these units. It's M over S over M squared. Well, M squared is the same thing as saying M times M. What happens is one of the M's cancel, and then what do you have left? Well, you have 1 over S over M. This S is in the denominator, and just like this M's in the denominator, so technically your units is 1 over M times S, okay? As I said, make sure the M and the S are different sizes. So this K's units is 1 over M times S. Okay, and there's your K. So the next section is to help you with the units of finding this K. They change depending on the orders, okay? Because our orders up here, they were both first order and first order. What happens if the units, the orders are different? So for example, what if I had a rate law that's K concentration of X squared, okay? Remember, that square goes for the number and the unit. So right here, I have rate as M over S equals K, and then I have M, but remember that M is also squared. So if I take this M and divide M squared, well, it's the same thing as saying M times M. One of those M's cancel, the S is in the denominator, and it comes down. So 1 over M times S. Now, I want to mention these units too. Sometimes AP will write the units with the exponents as negative. These negative exponents on the units just means that the units are in the denominator. Okay, that's all it is. I don't care which one you do, okay, but you got to make sure you understand what M to the negative 1 is and S to the negative 1 is, okay? So here's a little chart to help you with it. The one that we did was this one right here because they were both first order. Well, what if you only had, like, let's say like a rate equals K and then concentration? What if you only had one reactant and then it's to the first? Well, if this is M over S and this is M, when you divide, get that M over here, the M's cancel, and then look what you have, just 1 over S. What if it's to the third power? So I have rate, little k, and then maybe I have like x to the third. Well, that third goes for the number and the unit. So if rate is M over S over M cubed, well, it's the same thing as saying M times M times M. So one of the M's cancels, but I still have those M's together, M times M, which is called M squared times S, okay? Do you see a pattern? Every time the order increases, the molarity is first order or second or to the third. So if you actually did have like a fourth order, then it would be 1 over M cubed times S, okay? The only one that's not 1 over something is if it was 0 order, because here's why. Rate equals K. Because if you had something that's 0 order, you wouldn't include it in your rate law. And we're going to do one of those in just a second. So that means your rate is K. And rate is M over S. Okay? So that's a little way of helping you with the units until you become very familiar with it. Okay? Let's try another one before you do one on your own. What if we had 4 trials, 4 experiments? Okay? and I have an A and a B, I want to do the same thing. I got to determine the orders, okay? So I'm going to start with A. I want to change A, so I want to solve for A. So that means, making little notes over here, A's concentration has to change as B is constant, okay? Till you get the hang of it, you don't have to write stuff like that, but, you know, it helps right now. So when did B stay constant? Well, B stayed constant experiment 1 and 2, 2 and 3. Heck, I could even use 1 and 3. I can't use number 4 because 4 changed. So I want to pick 2 experiments where it makes it easy for me to figure out. Well, I'm probably not going to pick 1 and 2, okay? But probably I could already see right here 1 and 3. 1 and 3, that's much easier for me to see because I have a 0.5 and a 1. That looks like it doubled, okay? So I'm going to say using experiments 1 and 3. Could you pick experiment 1 and 2? Yes, you could. I like to pick experiments that make it nice even numbers so I can actually see if it doubled or tripled. So my concentration, 1.00 over 0.5 equals, now I got to come over here to the rate. Well, look at that. The rate didn't change. So 0.50 to the negative 2 over 0.50 to the negative 2. Well, 1 divided by that, 1 divided by 0.5, and obviously that's 2. 2, and because I'm solving for A, I'm going to call it X. Well, the same number divided by the same number, well, that's called 1. I don't need to plug that in the calculator. Well, now here's your question. 2 to what power is 1? Well, that's 0 order. And if anything is 0 order, that means the concentration of A has no effect on rate. So if it has no effect on rate, do not include A in the rate law. Because if it has no effect, there's no purpose to put them in the rate law. So this A is going to be gone. So now let's see if B actually does anything. So now for B, we want B to change where A is constant. Okay, so I'm just making a note. Make sure A is constant. Okay, so let me get rid of my little brackets here. Now, I have to choose experiment 4 because that's the one that did change. The question is, do I choose, so I don't know why it jumped on me when it makes those crazy shapes. Do I choose experiment, I could choose 4 and 3, I can go 4 and 2, I could go 4 and 1. Doesn't matter which one. Let me back up. I got a little happy there. Okay. So if I want these two to change, okay, sorry, I cannot choose 4 and 3 because 4 and 3 change. So that one's a no-go. Between 4 and 2, nope, can't choose that one because A changed. So that means I have to choose 1 and 4. Okay, my dogs have distracted me today. Sorry about that. All right, so A is constant as B changes. And then rate actually did change. That means B is going to be in our rate law. So I'm going to tell them using experiments 1 and 4. And big number over small number. So 1.00 to the negative 2 over 0.5. Okay. So 4 divided by 2, well, that looks like it's going to be 2. But you know what? Let's don't trust the brain today. Let's make sure we plug it in. And then 1.00 and then divide by that 0.050. Oops, I had too many zeros. 1 divided by 0.5. All right, so that's 2. So 2 to the y is 2. Well, that has an effect. That means y is first order. Okay? So now I found the order to each one. What's my overall? Well, my overall order is 0 plus 2, which is 2. Okay, I'm going to box these so that way I can make sure I have those answers. What's my rate law? Well, A had no effect. So my rate law is K and then B to the first order. And make sure you're putting those in brackets, not parentheses. Next one is I want to solve for rate constant K, and then I want to find out the units too. Okay. All right, so I'm going to tell them I'm going to use experiment 1 because I always like to use experiment 1. So I'm going to use these values. Don't care about A because A has no effect, but I'm going to need that number for B. Okay, so K, and then my concentration of B was 0.20 molarity to the first power. Okay, let me go back up. 0.200 to the first power, and then my rate, small number, 0.50 to the negative 2. And then remember, rate is m over s. Okay? All right, well, that 0.2 is to the first, so I don't need to square or cube it. So I'm going to take that K, and I'm going to take this concentration and divide it. I got to bring it to the other side. M over s. Divide by 0.2, big M. Well, the M's are going to cancel, so which means you only have your K, I'm only going to have 1 over S. But remember, as I said, you can even write it with exponents if you like, S to the negative 1. So let's plug that in, 0.5 times 10 to the negative 2, divide 0.2. All right, and it looks like 2 sig figs. I'm going to get 0.025. And there's my K. All right, hopefully it's getting good. I want you to try one yourself, okay? This is an AP actual question. I cut and pasted it, same thing. I want you to determine rate, the orders, the overall, so forth, okay? And if you do this right, let me check my work. I believe each one, let me check. Each one should have an exponent, okay? So that's your hint, okay? All right, so in conclusion, some big conclusions here, okay? It's not possible to determine anything about the orders from the balance equation, okay? You can't take like the coefficients and think that they're the orders. It doesn't work like that. So the coefficients don't equal the orders, okay? Orders have to be found experimentally, so you need some data table, okay? Beware, orders are usually whole numbers, but they can be fractions, okay? So this is very rare, and I think I only have like one practice problem that does that, but it not happened on the AP test in a long time, but we still got to show you. Zero order has no effect on the rate. So since any number raised to the power of 0 is 1, you don't write it in the expression. So if anybody's zero order, no effect, don't put it in the rate law. Usually the units of K, the little k rate constant, okay, you have to know the orders. You have to. To determine rate, okay, you need concentration, because when you write your rate law, K to something, I need to know this value. We haven't solved for rate yet, but we're going to. I need to know concentration and then to what powder. The rate constant depends on two things, temperature and the orders. So no matter what experiment you choose, it'll be the same K for every experiment as long as temperature stays the same. So you can use any experiment to solve for K since temperature is constant, which you know in AP by now, we're going to keep it constant because we're going to keep the math nice and pretty. But you know in life, it's going to change sometime, which it's going to in this chapter later on. I want to end up with what's the difference between 14.2 rate expression versus rate law expression. Okay, so 14.2 versus 14.3. Okay, so first let's deal with what we just learned today. So rate law expression, you only have reactants. Okay, reactants are only in the rate law. Okay, no products. Okay, whereas rate expression, all reactants and products are in the expression. Okay, with the rate expression, we had little t for time, and we had little triangles for change. Well, you didn't have that. There's no time and no triangles in our rate law. Okay? With the rate expression, all you need is a balanced equation. Okay? With rate law, you need data. You need experiment. Okay? Because remember, coefficients are not the orders. Okay? With a rate expression, let's just say it's a generic equation, A plus B makes C. Okay? The A, the B, and the C, the A and B were disappearing at some rate, as C was appearing. Okay? So with rate expression, it's about how the rate correlates with the other chemicals. So because A and B are disappearing, we take A and then change in A over time, change in time, equals, how does it correspond to B? Well, B is also disappearing, change in time, but C is appearing, so change in C over time. And I'm just going to put a little plus sign so remember disappearing and appearing. The only difference was if there, let's just say there was a coefficient on the 2A, then that 2 would go at the bottom. Okay? That's the difference. Okay? With a rate law, I need that data. So with my rate law, I have the word rate, little k, and then the concentration of A to some power, and then the concentration of B to some power. Okay? And then that's pretty much all it is. K units can change because they depend on the orders. Okay? Let's see what else. And I think that's about it. Okay? So notice the difference between it. One is looking at every chemical and how one rate compares to the other rate compares to the other rate. The other one is a rate law based off of data. Okay? But regardless, rate is always positive. Okay? Same thing with K. I didn't write it up here, but K, actually, let's write it up here. The rate constant, same thing, always positive. Okay? You can't have negative rate constant. Same thing with concentration, rate and concentration, always positive. Okay? You're not getting negative values here. Okay? Hopefully that was helpful figuring out the difference between 14.2 versus 14.3. All right, see you on the next one. And sorry about the dogs.